All right, I'm good to go. Happy Tuesday, everybody. Praise be the spiral. I just had a swig of the vodka and it's made me shiver. Oh, hope everyone's doing well. This is going to be a fun stream, I think. Finally got all the things I need together to do this racer. So gonna start thinking about the it's Wednesday, of course. Yeah. I forgot. I postponed, didn't I? So that's why. Um So yeah, happy Wednesday stream. It's an unusual one. I don't normally do Wednesdays. But yeah, this should be good fun. Let me start off by getting myself a vodka poured. So I've had this in the freezer for the past couple of days, since the weekend. I almost dropped it because I picked it up, and of course it's all kind of all slippery and icy. So it almost went smash on the floor. I'd been very upset if that had happened. It's also very freezing. Ow! My hand going on that. I hope everyone's doing well anyway. How's everybody's Wednesday been? It's actually raining here for, I mean, it doesn't surprise me. It's been so warm the past couple of days. It always tends to have one of those summer kind of rainstorms, and it's been so warm for so long. Uh, okay, let me just catch up with the activity. Thank you for the resub, SP. Thank you for the resub, Zendar, as well. Appreciated. Yeah, it's all good news. Even Doxter's almost got his Mega65 Nexus board. I've actually got Guest Drowns is here as well. So he wanted an orange case. I don't know how well that shows up. So that's the orange one ready to go. I'm just waiting on successful delivery, and so I'll probably post this on probably on Monday, I think, just to be sure. Give me a chance to test it because I haven't tested it yet either. Um, so yeah, apologies for this month's kind of delays. You can blame Norway for that. All right, let me bring up some windows that I need. What did I want? I wanted that window. Yeah, okay. And let me add some points to you all. I want to get cracking on this straight away. So what I'm going to do first of all is I'm going to explain the technique that we're going to use. Um, encouragement for his brain to think hard. Yeah, it's going to be a good one tonight. Thank you, Amok, very much for the bits, and thank you, How Price, for the follow as well. Welcome to the stream. Yeah, it can always blame Norway, exactly. Okay, so I've added bits to everybody. Let me start the races, and I'll explain what we're going to do tonight. Andy gifting the Shimmerbot thing as well. Small info Martin and time and me are in a makes this thing called most were only silently lurking and missing mostly until topics are tipped off. Oh, cool. I'm trying to think what what I want to add to the topics. But yeah, thank you. I look forward to hearing your guys' opinions soon as well. Thank you very much, Doxter, for the bits. I really hope you get your Nexus before the weekend and you can start having a play around. I think you'll enjoy it. There's very few minor differences between the Nexus and the real hardware. The main one being the color resolution is slightly lower. It's 4 bits per pixel, 4 bits per channel color on the Nexus. Thank you very much for the bits as well, monsters. Welcome to the stream. Yeah, so on the VGA output on the Nexus 7 only displays 4 bits of resolution in the colors. So you still use the colors as normal, but the lower 4 bits are basically ignored when you do it. So some of the color resolution isn't quite as good. And obviously you don't have joystick; you have to use numpad keys and stuff. So yeah. Did you not know that? I thought I'd mentioned that before. Yeah. Yeah, so the VGA out only supplies 4 bits of color on each channel. So you you don't get the full the full range of the palette. So thank you very much for the bits as well, SP175. Thank you very much for the bits. Side 2002 as well. Love the Mode 7s. Yeah, I think it's going to be. I think it's going to be brilliant. I really do. And Amok as well. Oh, it's a hype train. I see. You're all mental with these hype trains. Thank you very much, Amok, for the bits. So, what I've been doing after it started with the line drawings. Let me just quickly show you where the line drawing went. I think most people have seen this now. But the line drawing routine, let me rename this one. I was having some issues with it because on the last stream, because I made a maths error basically. And so that's why I wasn't seeing the issue that we were seeing before. So let me rename that. Thank you very much. Oh my God, you're all at it. Zendar, thank you very much. Dockster, thank you very much. Monsters Go Boom, thank you very much. You're all very crazy indeed. You're either very crazy or you really like the Turbo Outrun music. I've made the writing a bit bigger for you. Okay. Yeah. I have to stream more on a Wednesday if it's like this. Okay, so this was the original piece of code that I did on, when was it? Tuesday or Thursday? Tuesday, I think it was. Or was it Saturday? I can't remember. Anyway, I was having problem making this line go around, and the reason I was having problems making this line go around is because of this table that I'd set up here. So because you have to draw the line from the opposite direction sometimes, you have to kind of make these numbers go backwards, and I'd done this. I hadn't put brackets around this, and so obviously this calculation was completely wrong. So anyway, there we go. That was the problem there, and just spending a bit of time after the stream and looking at it, and it was just staring me right in the face. Thank you very much, Kenneth Mirror, for the bits as well. Appreciate it. You're all very, very crazy. So yeah, I've actually called this one clock hand because it is like a clock hand, and really it was just to show that we can draw a line in any direction. So then I took that kind of system and I turned it into an algorithm for the line. So I worked out that this is the algorithm for setting up the various kind of slopes and stuff. Any Resident Evil tonight? Maybe, I don't know. It depends. I'm quite tired. I didn't sleep very well last night. I was up till about 4 o'clock in the morning. I couldn't sleep, so I stayed up and just did a bit of coding just to practice a few things. But we'll see. We'll see. I'm in a good mood, so maybe. And thank you again, Amok, for the bits. My God, level 5, guys, you're crazy, and more from Dockster as well. Bloody hell! Cheers. I'm going to drink lots and lots of vodka now. Is there a reason the center point origin moves? So the center point origin isn't actually moving. What's moving is the end of the line. 5 sprites as well. My God. And the reason for that, cheers. Thank you, 5 sprites. The reason for that is a bug in the line code on the FPGA, which is occasionally you have to draw the line from the other end. The major axis, so the axis which has the most change in it. So if, you know, for a line like that, obviously the most change is along the X. Thank you for the gift sub to Quadrasil as well, Andy. So the line that the major axis should always be positive. If it's not, then what you have to do is you have to draw the line from the other end so it is positive. Thank you very much for the bits as well, and the gift sub to Acmafin, True Tonnant, 5 sprites, and Amok as well. Man, you're all crazy. Steps is missing the madness. So yeah, when you draw the line from the other direction, obviously it means that the end point is now you know that you're not drawing from the center, you're drawing from the end of the hand. And there's a bug in the line drawing that we touched on last time, where one of the pixels, the very first pixel, is drawn twice before it starts doing the slope. So what happens is you end up with the endpoint not quite meeting the middle. So that's why it looks like it's jumping around a little bit. It's a very minor bug. It's something I've noted with Paul. He knows about it. There is a bug listed for it. I think there's a bug listed for it. At least I've created the test program. I might have to check if it's listed or not. But it's there, and that it's what causes problems, but it shouldn't be a major issue for what we're going to do tonight. So what I did is I took that line algorithm that draws this clock kind of hand going round, and I worked out some pseudocode. So based on the x and the y positions, x1 and x2. Thank you very much, Grey Defender, as well, for the bits as well. You're all completely mad, completely bonkers, and you're just trying to make me drink vodka fast, I guess. So yeah, I worked out that this was the pseudocode because we need to know which is the major axis, whether the other slope is negative or whether the minor axis is negative or minus, and whether negative or positive. Whether we should be running from the start of from x1 and y1, or from x2 and y2. So which end of the line we should start from. And then calculating the slope. So this is what I come up with. It took a little bit of a while to figure out what the connection was between all the pieces, but this is basically how it works. So then I turned that into a routine, so a relatively fast routine where you can pass it an x1 and a y1, an x2 and a y2, and call draw line fast, and it will fill in the DMA, set the appropriate values up, and call the draw line function. Oh my god. 5 sprites, thank you very much for the double bits, and Skunk Monkey as well. Cheers very, very, very much. I'm gonna have to buy you all lots of drinks when we eventually get to meet up and have drinks, which we will do at some point when the pandemic's over, or at least, I mean, if it's never gonna, it could never be over as far as we know. How many bits is that now? I have no idea. It doesn't tell me how many it is until after the stream, unfortunately. It's quite a lot though. A lot of mental. Wait, did I understand that you can have a texture on the line? Yes. So when we were doing this routine, this could only draw one color. So we tried to draw from a texture and it didn't work. But now we've after speaking with Paul, he's changed the routine, and it now is capable of um, reading from a line, a random line, an arbitrary sloped line, and drawing to an arbitrary sloped line, and you can turn them on and off, and that's what we're going to utilize to do the mode 7 stuff tonight. Thank you very much for the follow, Bramado. And of course, we all meet in Norway. Well, we can meet in Norway, but we'll all arrive like 3 weeks late, I think. That's about crickets, which sound out and boom. Yeah, if you need anything, just just pester me. It does seem to be. I do seem to have a bit of sway, which is good. I think it's kind of growing as well. I think more and more people are getting involved now, and I think there's definitely some incentive, especially with the competitions, to get the things that people want working. So I think that is kind of changing a little bit. So that's kind of good. Oh, I got an emote from that hype train. What did I get? Thank you very much. I got a little choo choo cat. So yeah, anyway, I took that clock hand thing and made a line drawing routine out. It's not very optimal. There's things I could change in it, and I will change them at some point. But this was just to demonstrate that I could draw arbitrary lines of any slope at a relatively decent pace. So this was the second thing that I made, which is kind of like a Windows screensaver quicks kind of thing. So the white raster bar at the bottom is the bitmap clearing, and the red one is all the lines being drawn. There's 128 lines being calculated and drawn every frame here, and it happens in around about 30 to 40 raster lines. It takes about a third of a raster line to calculate and draw a line. And this is just a list that's been shuffled every frame. So it moves one of the lines and then moves everything down the list. And the colors just based on the index. So there's a few little bugs in this that have cropped up, and I think that's just down to the accuracy of the hardware multiplier and the hardware divider. Because at the moment I'm just doing the division and I'm not waiting any cycles. So here I'm not doing any cycles. I should be waiting a few cycles here instead. But I'm not doing. But we'll be doing that in the foot there. You see, it goes all wrong. It goes, I think, because as well, it sometimes it goes outside of the bitmap area and ends up writing into areas that it shouldn't be writing in. But the general concept is there, and it works fine. So from that point on, I basically started speaking with Paul about what we could get put in. Asking for the ability to instead of just fill in a line with a color, to read the pixel values from another line somewhere else. And so that's what Paul did. And I do have some example. In fact, is this? Oh, I'm not even sure this will work. Let's try it. I'm not sure what this is or if it will work. We shall see. Okay, yeah. So this is just a grid image that a PNG that I just took from the internet and put into Asaprite. You have to save out the image in exactly the same format as a bitmap on the C64 and on the Mega65. That is, you have to treat it as characters basically, and you do it in the same way that you lay out the screen for line drawing. So you do characters going down in strips. So you do the same thing with the image, and that's what I did. I changed my Asaprite script to do that, to take a PNG and to convert it into a byte stream that follows that pattern. So 8 pixels across, down a row, 8 pixels across, down a row, all the way down to the bottom of the texture, and then back up to the top after to 8 pixels across and repeat. Um, this is actually taking that image, it's taking it lines that go down on an angle, so lines that go on a 23-degree angle through the texture, and then drawing them horizontally on the screen. So this proves that you can skew a texture by reading it from the screen and putting it back. So with that fix in place, I started looking at doing Mario Kart sort of things. So what I did is I knocked up this little demonstration to kind of give me an idea of what I needed to do. Let me find it. It's this one here. Just refresh and make this as big as I can get it. There we go. I don't know how easily you can see that. There we go. Probably not the easiest thing. So, is the DMA implementation 100% perfect for what you want to do? It's okay. There are some things I would like to have seen in it, but there's nothing. It's capable of what you see on the screen now is perfectly capable of happening. Um, but there are some limitations which mean we have to do some stuff extra, and I'll describe those now. So the way Mario Kart works is pretty simple. You have a flat texture like this. So this is a 1024 by 1024 texture. It contains the entire track, as you would if you've ever played the original SNES Mario Kart. That's the original track from that. And what happens is you pick a point on the track, which is represented by this kind of cone here. You imagine the point being at where these two lines meet. That's where the player is. The line, the horizontal line closest to that point is what we call the near plane, which is this slider here. Changing this slider allows you to kind of move the near plane and do various things with it. For most cases, it's just going to be 1 or 0. I've been using 1. It seems to be fine. I don't think 0 is actually possible in this slider. It's not. And the line at the far side is called the far plane, and that's this one here. So if we move the far plane closer to, let me turn the play multiplier off. I'll explain what that's doing later. So if we move the far plane closer to 1, then what happens is the this plane here gets closer to the camera, and you end up with a view which is of just basically a smaller piece of the road in front. And then as you move the far plane backwards, you start seeing more and more of the map as the camera basically pans out to a longer view. It has the effect in the game of raising the camera up and down. So in Mario Kart, when you jump around corners, that's how they do it. They're just moving the far plane slightly as you jump. So move the far plane and you've got to jump like that. Let me reset and turn this play multiplier off. So that's the near and far plane. So these lines that you can see, these represent what's being drawn on the screen. So each one of these horizontal lines is a line of pixels in this display. So the display starts at a position here, which is the maximum view height. If I move this up, it starts at the top of the screen. The view height is 200. If I move it down, then the view height becomes very small. And this has the effect of kind of tilting the camera as we move up and down. So you pick a nice kind of view. So I pick these values. These work kind of well. And you set your you set how much of the screen you want to be rendered, and you set your near and far plane. Then the next thing is the field of view. So this is the angle. So this is how far to the left and how far to the right you can see. So if I move the field of view wider, so as the field of view, so this isn't degrees, by the way, this is fractional in one rotation. So 128 is half a rotation. A full rotation is 256. So this is 180 degrees field of view. So this is a 90-degree field of view. And you can see that's the angle that these two lines create. So a wider field of view will mean you can see more on either side, but everything else will look like stretched and further away. And as you move the field of view inwards, you'll appear to go closer, lower and closer to the track, but you'll see less at the sides. So this was originally what I just had. I just had these 4. I didn't have these other 2, which I'll explain shortly. And that basically means that every line on here, so starting from the top here, the top of the viewport, takes the furthest away line, which you can't actually see here. And I'll explain. No, there you go. You can't. Takes the furthest away line and basically draws that a line of pixels across the screen. In one single line of pixels. Then it goes down a row of pixels and then it takes the next line and draws that. So as you can see, in the far distance, you're not seeing very much. So we can't really see the coins here. We can see a couple here, like 3, and that's because this line is going through 3 of them. So we see 3 pixels representing those coins over here, but that's the only line that goes through there, so we won't see any more than that. But as you get closer to the camera, the lines get closer and closer together until you're at a point where you can see all the detail that makes up a piece of the map. So you can see the line that goes over the line, the finish line is made up of maybe about 4 rows of pixels in the actual image, but because the lines are so close together, we're scanning the same lines more than once, and we get this we get this larger version. As you can see it zooming in as we get closer, and it gets larger. So this is how Mode 7 works on the SNES. Yeah, pretty much. Yeah, that on the SNES it's all done with hardware, so they have a special chip that does this for them, so the calculations are a lot easier. Why is it called Mode 7? I guess that's just what the mode was called on the chip. I don't know why it was called that. But yeah, I assume it's just what it was called on there. It was all done with 3D maths. No, there's no it's all just very smart use of 2D rasterization. So this all looks very good, right? And this looks like this could quite easily work using the DMA system. However, there is a small problem. There's 2 problems here. Firstly, these lines are all varying lengths, right? So I need to take this line and I need to draw it to the screen. Now the screen is 320 pixels wide, but this line could be whatever length it could be. It's really big when it's far away, and it's really small when it's close to the camera. And the problem with the line drawing algorithm is it takes a fixed width and it reads the same amount from the source as it does draw to the destination. So the stepper along the major axis is always moving 1 pixel at a time when it reads. Likewise, it's always drawing 1 pixel at a time when it draws. The actual DMA fractional stepper doesn't have any effect on this particular mode of drawing. So we don't have a way to shrink this line to fit the width of the screen, or to expand this line to fit the width of the screen at the bottom here. So that's the first problem. And we're going to solve that by using a second buffer. So what we're going to actually do, let me show you in here. So this is the map. Let me take a new image. I'll do a very small image just to demonstrate. So what we're going to do instead is we're going to take those lines and we're going to store them in memory sequentially. So say the first line's really long. I'm going to draw the first line in orange. This is the first line in memory, right? And then the next line is a bit shorter. So it kind of looks like this. And then the next one is a bit shorter still. It looks like this. And actually the gaps will between each one will kind of shrink over time, and you'll end up with a curve, kind of an exponential curve sort of thing. So we're going to draw them like this, and the reason we can do this is because we can basically we can take a source set of data from the texture read, and we can store it linearly in memory. So this is what we'd be doing here. We'd be storing each one of these linearly in memory. But then we can do the opposite. So we can also take that line, and we can we can take that line and read it at one length, and then store that on the screen at a fixed width while scaling this side. The only thing we can't do is we can't scale any line while we're reading texture data, or from the texture. We can read it if the texture is set out like this, but unfortunately we can't set the entire kind of map out like this. So we have to take a segment at a time. We have to take a frame at a time, lay it out in memory like this, and then scale it to the screen. So that's a little bit of a kind of a downside to the system, and it's a little bit of a limitation of the system. And it's simply because the DMA stepper doesn't function the same when line mode is turned on. But it's not a huge problem for us. It just means there's one extra DMA step, and it's that DMA step, that final DMA step of taking that data that's laid out linearly and plotting it to the screen that we're going to work on tonight, because it will be the easiest one to test when things are working. Once we get that working, we can work on filling that memory linearly. But that's the bit that we're going to do tonight. Now, there's one other thing, and this is the reason the plain multiplier is in here. Well, actually, there's two things. I'll do the V resolution first. So one of the things that's going to make this kind of slow is how many times we have to read lines, right? So it's actually two things. It's the length of these lines is going to slow it down. So the longer these lines are, then the more time the DMA needs to spend reading them and drawing them into other areas of memory. And the second thing that's going to slow it down is the number of lines. So there's two things that affect the number of lines. One is how high we make the view height. Obviously, this is kind of hard to change. We can't do a lot with this because we need the view height to be about right for a Mario Kart game. So this has to kind of be roughly what you'd expect in a Mario Kart game. So round about here is fine. The way the rendering works is if it finds an edge of a map, it just repeats the same color from the edge of the map infinitely. So we get what looks like a green grassy horizon. And all it is because when it gets to the edge of the map, it's just where these lines go off the map, it's just drawing the edge color. But the other thing we can do the other thing that would help speed this up, as well as reducing these lines and reducing the number of lines that we show on the screen, is to reduce the number of lines by repeating certain lines. So this is what vertical resolution is. So a V resolution of 1 means every line is drawn once. A V resolution of 2 means every line is drawn twice. So it draws a line and then it repeats it underneath. And you can see it halves the number of lines that we draw. You can see the lines here. they half as we do this, and the resolution drops down. So it's kind of like going into a low res mode. So this is an option if we do have problems with rendering, we can just reduce the number of lines we actually read, and just duplicate lines as we go down. How did you do this prototype? Did you code from? Yeah, it's just a JavaScript. It's quite a short JavaScript program. It's not really a lot to it. So um, I can share this as well after the stream, so you can have a play around with it. So yeah, there's the vertical resolution. You can see as well, if we knock it right up, obviously the resolution is super low now, but the number of lines we draw is way less. So 5 times less lines. So we have this option for changing this as well. But the biggest problem that I think we would face is the length of these lines. So what you can't actually see here is if I just keep going off, you'll see these black lines, they keep coming. They're further and further apart, but they do keep on coming. And there's another one there. So this is a problem, because what this means is if I'm on the screen on the track at this point here, then the furthest line, the line that's showing right on the horizon here, could be magnitudes, hundreds of times the width of the map. So it could be 5,000 pixels long. That's too many pixels. That line has to be drawn linearly in memory so that it can be scaled later. That's too many pixels. So what I decided to do was have a play around to see if I could reduce that somehow. I'm sure that resolution changes how Super Mario Kart did the screen transitions. Yeah, possibly. Possibly, yeah. It's a good idea. We could probably do that like that in the game as well. Just get some drink in me. A bit more. There we go. So I wanted to try and find a way to reduce these number of lines. So I introduced this thing called the plane multiplier. And what this does is it takes the far plane, multiplies it by the plane multiplier, and that's how many lines it draws. So if you count from the bottom, there's 60 lines here. So 1 times 60, 120 here. And what that means is even though my view height is higher, you can see it clips. It stops drawing when it gets to that point. And you can see the effect that has. Now the lines are within the map. So the last line there is still within the map. But obviously it means our draw distance is less. So this is affecting our draw distance. But what we can do is we can find a nice position, something like that. Actually, I had it already set up. So yeah. So I found this position, which is 127 long. And you can see the very last line is fits within the map. So there's going to be no case where the line is thousands of pixels long. So this allows us to to limit how many pixels we have to read from the texture in order to be able to do the scaling later on. The problem really does come down to the scaling. It's something I hope in the future we will see added to the DMA, which is the ability to step through the source texture fetch using the DMA stepper as well as the slope stepper. I realize that would complicate things quite a lot in the DMA, but I'm hoping that's something Paul can add later on, because it will have a huge impact on the speed. The only reason we need to have this intermediary buffer is because we don't have the ability to scale that texture on the fly while we're reading a line across. So for most things, it's not going to matter, but because of the way we're trying to do this, it's very important that we have this scaling. So we do have to have this kind of secondary linear buffer in memory. Anyway, cheers, guys. But yeah, thank you for all the crazy bits and subs and stuff tonight. You're all absolutely mental. But I appreciate every single one of them. It's always really nice. Okay, let me just check. Right, let me figure out what to do first. Okay, so what we're going to do first. So this is going to be the example that we use. The code is, I mean, it's a little bit messy because it's been thrown together relatively quickly. It's not it's certainly not production ready code or anything, and it's not using it's not using like WebGL or anything. It's just straightforward source textures basically on a canvas. The one thing I did do with this is I wanted to make sure that this worked with a fixed point stepper as well. So I've created this line stepper which does the same job um, that the DMA stepper does. So I just wanted to make sure that the system would work the same. So I'm using nothing but integers to describe uh, the the line slopes and stuff, but um, it's really just to make sure it could advance through the line. So there are some kind of divisions in here which obviously do return, yeah, here sort of thing, uh, that do return floating point numbers. So there are some rounds in here to make up for that. But the 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 concept is roughly the same, and it's going to be pretty much kind of the algorithm is going to be taken roughly line for line and converted into assembly. But I'm going to do it we're going to work backwards on this. So what we're going to do is we're going to start with the intermediary step. So we're going to make a, a, a format, a kind of memory data format that we can read um, and output that to DMA lines, which can then be drawn to the screen. So we'll start by going through that. Let me just get some smoke in me and some of this in me, and we'll do it. But hopefully that kind of explains how this works. And as I say, I'll share this code afterwards, so you can play around with it yourself. It's very simple. The concept is pretty well known. I mean, obviously nowadays you wouldn't do this like this at all. You would use WebGL, or you would use, whatever your hardware accelerated graphics engine of choice is, and do this just with a plane. In fact, you wouldn't even do this kind of engine now. You would do proper 3D. But if you did want to do this now, you would just do it with a 2D plane. So you would just with a plane in 3D, but just like laid flat, really. Maybe the easiest way to do it, and then you get all filtering and stuff, which you don't get in this mode. Um, but yeah, I'll share this after the stream, and you can have a play around with it. Okay, so let's set up the file first. Let me grab a make file. New file, paste that there, save that as make.bat. We don't need the Asaprite script just yet. We don't need that just yet. We don't need to make the disk. It should be main 2s. Why is it 2s? There we go. Okay, so that's our make file. Let's do the code over this side. So let me just close all of these down. Actually, let me take the first couple of lines on this up to all right, I'm going to take some of this. All right, so what I'm going to take up to here, I'm going to create a file called main in here, put it in here, file main.s. Save, go. Okay, so this is our basic setup. Oops, well, multi-cat cursor on, that's weird. I do need to upgrade to Sublime 4, because I was reading about that, and it's actually very compatible with 3. In fact, it's kind of just it's more like a massive enhancement to 3 rather than a new version. So um and it looks pretty good. The autocomplete stuff looks like a major upgrade. So okay, so these values are going to stay the same. Interplanet Me, thank you very much for the follow. Welcome to the stream. Cheers. Yeah, it's unusual actually that Steps is not around, isn't it? Yeah, no idea where he is. It's missed a good one tonight as well. It's been interesting stream. All right, let me grab some of the setup functions in here. So I'm going to get the screen base, the clear bitmap, clear color RAM. I think they're all fine, and it's got these ones as well. So these are routines that I was using previously. I'll explain what each one does very quickly now. Don't need that there. So this init screen and color just basically sets up where the screen base is. So its default is 0800. We're just moving up to 8000. And it screen and color. It also sets the logical and physical row sizes up and calls clear color RAM, which is just a quick DMA job which just fills color RAM with zeros. Hey Zappy, welcome. Oh, that reminds me as well. For those who have ordered for those who have ordered Dot Cosmos, that is now shipping as well. So Zappy's been very busy creating lots and lots of boxes and cartridges and stuff. So thank you very much for all your work on that. So yeah, that's what init screen color does. It just sets the color RAM up and sets the screen up. The other thing we need to do is clear the bitmap. So we have the screen base is automatically set up with the bitmap. So the bitmap is basically, I'll show you now. If I put a 0 in here, you will see it. And if I just, I'll call the clear bitmap. It doesn't really matter that you're not going to see it anyway here, but just a note as well, none of this is going to work on the emulator yet. It's something I'm hoping we can get fairly soon, done fairly soon. I will try and work closely with LGB to get this stuff in there, so you guys can kind of mess around with this as well. Let me turn 40 column on. I should set all the colors up in there. In fact, why are we not setting those up in knit screen? That's where that should be set up. That should all be set up in here. There we go. There we go. So this is the layout that we need for the bitmap. So what this is technically doing, it's just setting out all the characters from. I mean, at the moment, it's setting out the characters in the default ROM set. But what it will actually be is the characters at index 0400 onwards, 0400 to like 07FF. Um, that's character indexes, not memory addresses. The memory addresses are that time 64, and they work from left to right in strips going down. So you can see you've got the at symbol, which is 0, then A, B, C, D, E going down the screen like that, and then it repeats across. This format is needed because, as I've explained before, you need to have at least one direction which is consistent in the way it advances. So by setting the screen out like this, you know that you only have to add 8 to any position on the screen. If you add 8 bytes, 8 to the memory address of any pixel on the screen, you go down one row wherever you are on the screen. Adding 8 to it will always go down one row, and that's why we lay them out like this. If you tried to lay them out horizontally, then it would be different, depending on where you are. If you're on the edge of a character boundary, then obviously adding 1 would not take you to the next row or the next column, but it would take you to kind of somewhere else within the character block. So we have to lay them out vertically like this, and it's exactly the same for the textures when you're reading textures as well. They need laying out like this, as I said. So that's why that's like that. And basically, when that's laid out like that, you can then treat the memory address 100. So what we've got here. As bitmap data. So the same way you would treat a Commodore 64 bitmap, it's kind of like that, just some slight kind of, instead of going horizontally, the strips go down before they go across. But you treat this, even though it's a character set, you can then treat it like a bitmap. So the other thing that you'll note as well is I'm only using 128 lines because it divides nicely and it kind of matches what we've got in here as well. So a maximum height is 127 here. If I just make it 128, That would be better. There you go. So that's exactly the same screen size in terms of the amount of, the percentage of the screen that's been taken up by the track and the what's the sky. So that's the same here as it is on there. And that's done just by setting the screen RAM up ahead of time. So we just use assembly time for loops to work this out. So we do 9 rows of blanks and then 16 rows of characters, and we get that. Okay, so if I put that back now, we should have a bitmap, and you won't see anything because it will be clear. There it goes, completely clear. If I was to change this to a different color, like so, then you will see that it would clear to that color instead. And our bitmap will look, in this case, white, because it's still using the palette from the C64 at the moment. So this will be red. But you can see that this is just a bitmap, and we can fill this in with whatever we want, and it will be treating. Now, the good thing about this this kind of engine is that you don't have to clear the bitmap ahead of time, because you scan in the entire bitmap. Because you're drawing on every single line, you don't have to clear the bitmap. You don't have to do anything to that bitmap, as long as your bitmap is just the road. So this is why I've left the blank at the top. So that could be the sky, for instance. If I was to change this to E here and make this 5. There you go. So now anything I do on the bitmap is just the bitmap, and the sky is completely separate. The sky is not even, it doesn't have to be cleared or rendered or anything. So the ground never has to be cleared, because every frame you just redraw over everything anyway. So it works out really, really, really well for this kind of engine, and saves you a little bit of time. I mean, it wouldn't take a huge amount of time with DMA to clear that. You're probably looking at maybe about 8, 9, 10 raster lines or something, but it's still, it's still work you would have to do. So normally, but you don't have to with this, so that's great. So what we want to do is we want to take some sample format, and we want to draw it to this screen. So the way I'm going to do this is I'm just going to create a really, really simple format, and the way it's going to work is the first byte is going to, in fact, let's do this let's make another file and let's import it. Let me do all the imports here. So we're going to import a file. I'm going to call this I don't know what to call this. Do you know what? I'm just going to call it mode 7 buffer, because that's what it is. Okay. I'm not gonna put should I put a namespace on? I will put a namespace on. All right, but I'm gonna use lowercase as well. I'm just gonna call it M7 buffer, so I don't have to type mode 7 every time. Okay, so what the mode 7 buffer is going to do is allow us to read. Well, we'll put some demo data in here first, but we're gonna read this data and create a DMA list out of it. So the way this is going to work is you're going to have a DMA list, which is the length of whatever our screen height is, right? So we would define some constants somewhere. So I guess we could define the constant here, or probably better is we probably define it before we do any of these things here. So if I define it here, I wonder if I can use constant here. So we're going to say view height, and that's going to be 128, because that's the height of the area that we're going to draw. It's the height of our bitmap in pixels. So we're gonna use that, and all the variables for this I'm going to prefix with M7, and in fact I'm going to use. Actually, no, it's constant, isn't it? So I am going to use capitals. If I've got it marked as a constant, I'm going to use it as capital. So even if it's a label, but it's acting like a constant. Okay. So then what this means is there will be a DMA. So let's create the DMA first. Let's do the copy buffer to screen. Copy, let's just call copy buffer DMA. And so this is going to have, obviously, it's going to have the run DMA job. So we're going to use some macros in here, but there will be a lot of stuff that I won't use macros for because it's just not going to make any sense when we're changing so many of the values. So, but that one is definitely going to be the same. This is pretty much always going to be the same whenever I do one of these DMA jobs. It's always going to look roughly like this at the beginning. But this is where it changes. So now I need to create a list of DMAs. So um, I could just create one DMA and just keep changing it. But then what you have to do is after every DMA, you would have to change the values and then run the DMA. Oh, actually, maybe this could work with. Yeah, actually, it might work. It'll save some memory as well. All right, we'll do it that way then for now. So the loop is probably going to be up here. In which case, what we'd do is M7 view height. There we go. And then we run the DMA job. Then we decrease that, and if that's not equal to 0, then we jump back to here again. Okay, so now we're running this DMA job once for each line on the horizontal line on the screen. So the thing that's missing here is we need to fill in the values. So I'm just going to put to do in here. We'll come back and fill this in a second, but fill in the DMA values. The other way to do this, of course, is to use chained DMAs, and that might be the way to do this if, or at least with certain no, it's probably all right like this actually. Yeah, all right, it's fine like this. Okay, so now we need the line DMA job. So let me just go and grab the textured line DMA job, which I do have already somewhere. I think it's that one. That one. Yes, this one. All right, let me copy this entire job, and I'll go through it a step at a time. So no, I did some tests over this side, so that's why I've got a lot of code to draw from. Okay, so as we mentioned before, DMA job consists of a list of options, sorry, a header, a list of options, and then the job data itself. So the DMA header is quite simple. Just defines the source and target megabyte bank. Because our source is going to be in the lower megabyte, and also the sorry, the tip came off my headphone. And also the destination is going to be there. Both these can be 0. For the most part, these will always be 0. There is one exception, which is I may, when it comes to reading the main texture, I may move that up into attic RAM. So the limitation of the normal RAM, the RAM that's the fast RAM, if you like, is that it's only 384 kilobytes. So you've got your 64 kilobytes of code space, which is the normal 0 to 65, so to FFFF, which is the same memory that we use on the C64. And then you've got 320 kilobytes of memory after that, which you can use for pretty much anything. The VIC force can see all of the memory everywhere there. So that means that if you want to do DMA, DMA is 4 times faster in that area than if you use the attic RAM anywhere else. Hey, Cosmin, thank you for the resub and welcome. FFFF, yeah. So obviously you want to try and do as much as you can in the fast chip RAM, because the upper attic RAM is 4 times slower. However, because you've only got 320 kilobytes down there, and that's for everything. That's for your everything that the VIC4 needs to see needs to be in that block there. So you need to fit your sprites, your font, and everything into there. Now, the bitmap that you can see on the screen now is taking up about 2/3 of the area um, from. Oop, let me just put that back where it should belongs. From 100, from 10000. So that bank is kind of, we can't really use that area. That's being used by the bitmap. Possibly some sprites would go in there. There's really not a lot of room. So that means the biggest block of contiguous space is after this. Now, a 512 pixel by 512 pixel image using index colors, which we use on the Mega65, is exactly 256 kilobytes. So that fits neatly from. And let me just write this in here. Let's call it. Let's call it map texture data, and that goes there. Now that's going to run all the way to the end of. Oh, is that a new series, or did you already have the new series? Uh, hey, steps. um, yeah, so that basically fills the rest of that memory. So that means there isn't a lot of memory left, and the biggest texture we can have if we use fast chip RAM is 512 by 512. Now, the image that I'm using in this is 1024 by 1024. So 512 by 512 would look roughly like this. A bit lower detail. In fact, a little bit less detail than this because there's no horizontal scaling here. So only vertical resolution scaling, not horizontal. So it would be like as twice as bad as this still. So that means in order to get a bigger texture, so say we want to use this texture, we'd have to use the attic RAM. So that's an option I'm leaving open, and I may do that if it's fast enough. But it's not something I'm going to do straight away. I'm going to go for the fastest approach first. If it turns out that this can be run, the DMA can be run very quickly within one frame, then we'll move it up into attic RAM and move the texture up there. It only has to be the texture that can be up there. The intermediary buffer can be in the lower area of RAM. In fact, I would recommend it's in the lower area of RAM. But yeah, this should allow us to at least have 512 at the moment. So that's what we're going to work with first, and then we'll upgrade to the high one later. Okay, so let's go through. So we've got the header, and what do we need to do? Okay, so what we're doing here is we're taking lines which are not stored in normal format. So we're just taking horizontal slices of line. So we don't need to do this line draw for our source. This is the oh no, sorry, this is destination. We do need it for destination, but we don't need it for source. So let's get rid of that. So we can get rid of the source one because we don't need that. But we do need it for the destination, and the destination just says we're using a line draw. So whatever we read in needs to be drawn in a line across the screen. That line is an X a major x-axis line. In other words, it increases more across the x than it does in the y. And the y is not negative. In fact, the y is completely static. There's no slope at all here. This means that we need to set up a column byte. So the column bytes tells us how many bytes it is if you go from if you look at the way that the screen is laid out and you've got those row of characters, if you go from the right hand side of the top row of characters and move 1 pixel across into the left hand side of the next row of characters, how many bytes across is that? Well, that's just basically the amount of bytes in that strip minus 8. And so we have to set that, and then everything else we set as 0 because we don't have a slope, and we don't need to advance the y in any way. So all these are going to stay the same. Good night, Quadrasalt. Thanks for joining the stream. Cheers. But we do need to set up another step. I need to find a mega book. Hang on, let me get that. Which is a source stepper. So this is our destination. Let me type that there. In fact, let me do that here. So this is all our destination stuff. And because we're using line draw, this is all we need to grab the stuff to draw it on the screen. So this is going to draw all the way across the screen in one go, and the length of that is going to be down here. I'll come to that in a minute, but this is basically just going to start from the left hand side and draw a straight line across the screen. But the data for that needs to come from the source. So that means we'll set the source up down here as well, but there are some information about the source we need. So one thing we do need to know is we need to know the source skip rate, which is in 2 bytes, 82 and 83. So 82, no, right, 83. So this is how quickly we move through the line. So if the line is 320 wide and we want to draw it to the screen, which is 320 wide, then every time we advance through the source line, we're moving 1 pixel at a time. So this is our fractional, and this is our integer. So we move 1 pixel along the major axis for every pixel we draw on the screen. However, if the line was half the size, so if the line was 160 wide and we want to draw it to the screen, which is 320 wide, then we need to advance by half a pixel at a time. So we would change this to be like this, and this would change as we move through the line, through each line. So each line is going to have a different value here. So that means we need to set this up on the fly. So we're going to add a little label into this one, and this is going to be source fraction, and that's going to be star plus 1, and we'll have source integer, which is star plus 3. So these are the two values we would need to change in order to make sure that the entire line is read from beginning to end and scaled properly to fit the screen. And this is the problem with the line draw. If we use line draw on the source as well as the destination, then these have no effect, and that's what's making us have to have this other buffer as well. Right, I need some more vodka. Who's this? This is your series, isn't it? Steps. I think you made this one. Yeah, it was you made this one. Also, what's with the Christmas tunes? Is that Cosmin? Merry Christmas, Cosmin. It took me a long time to realize that. I think it's been going on a while, and I've only just realized. Okay, so we need to adjust the source on the fly. So that's one of the things we're going to do here. So I'm just going to write, these are the things that we need to do. So we need to set source fraction and integer. Now the amount that we have to move is going to change all the time, because unfortunately it's not the length of the line. Oops, let me just come back here. So this is the line we're talking about that needs scaling to the screen. So say this is 640 long, then this needs scaling to be half the size as it moves across here. However, this is not the length. That's not the length that we're looking at. The length that we're looking at is the length of the major axis here. So actually the length is this angle here, is this line here. So if you imagine this being the hypotenuse on a right angled triangle and draw a right angled triangle here, then the opposite side here is your y, and your adjacent is your x. It's the adjacent in this case. It would be the opposite in that case. Whichever is larger out of those two is actually the length, and so that's going to change as we move around. That's going to change in size. So we can't have just a fixed list of lengths that apply to our particular near and far plane, our field of view, and all the other parameters that create this kind of stream of lines. So unfortunately, that's not something that we can create a table for, because that has to be calculated on the fly. But we'll go through the hardware math unit in a minute, and I'll explain how that works, and I'll make some macros for that, and I will put that into the Mega65 macros, so you can use that, and hopefully that will make things a bit easier for you. Crichton. We should have made Crichton. We should have made Crichton his full name as well, even though he thinks it's a bit jerky. He calls it. Does he call it jerky? Oh, I can't remember what he calls it. We'll soon be closer to Christmas than the last one. Yeah, that's true. Yeah, only a week away, isn't it? A week and a bit. Yeah, it's something like 2x4b or something like that, or 4p. I can't remember what his full name is. His last name is like 2x4bp or something. So I'm sure somebody can post what it is. My God, you've nearly found all the backgrounds. I really, really need to get more backgrounds. 2x4b. I remembered that. I'm impressed I remembered that. I remember it had a P in it as well, but I don't remember the other bit. Thank you, monsters. 2x4b 523p, but he thinks that's right. He thinks the 523p is jerky, something like that. So there's two values we need to fill in. These will have to be calculated based on the line size and the target. So let's move down to the other things we need to change. So once you've got all the job options in, job options are basically just a byte followed by a parameter. The full list is in the manual, and it's grown exponentially since we added the line textures in. You have a claim to fame with Red Dwarf. Okay, what's your claim to fame? Season 1, the warning screens and computer text was done by Joffa. Ah, okay, that's cool. That's cool. Let's change it one. Yeah. Is he Dolores Abernathy? Ah, okay. That's really cool. I wish because I was a little bit too young when Red Dwarf first came out. I'd watch it, but I didn't really understand it properly. And it was only by about season 3 or so that I started to kind of get the humor and kind of understand it. So I'd go back. My friend had all the VHS cassettes box set for the first 2 seasons, so I lent those off him and watched them again, and then read the book as well. And from that moment, I was just hooked on it. So yeah, it was kind of cool. Okay, so the other thing we need to know is the source and destination. So this is where the once the job options are finished, well, you have to pass a 0 by, and this is just to tell the DMA magic chip that there's no more DMA job options. The next data that you read is going to be the actual job data itself, and this is going to contain the size and the destination, whether it's a copy or a fill. So let's set this up here. So is it the last request? It is going to be the last request because we're not chaining at the moment. We may change that. We may, depending on speed, we may change that. So let's just set it up to be last request and copy. So, oops. So the default job type is a copy. and that's with no bits set. It's just a copy, and it will also be the last request. If you set the bit 3, so if you set bit 2, so if you do that, then it basically says that it's the last request. So bit 0 is whether it's a copy or a fill. I can't remember what bit 1 is, and bit 2 is to do whether it's the last request or not. If you pass in 0, 0 here, so this is the actual job data. The job data is always the same format, always the same size, always the same amount of bytes in it, and it immediately follows the 0 at the end of the job option list. The first byte is the type and whether or not it's the last request, which is, I said here, it is the last request and it's a copy, so 0, 0. Then we need the size of the copy fill. Well, our size is quite easy. Our size is the width of the screen, so that isn't going to change with the viewport. So I'm actually what I am going to do is I'm going to put this into a constant in here. So I'm going to call it view width, because we've got view height, and I'm going to set that to 320. So by default, it's just going to fill the entire screen. Again, we can shrink this down, right? So if this is becoming problematic to do 320, we can shrink it down slightly and change some things to make things run a bit smoother. But I think we should be fine with that. So that's quite easy. That's just M7 view width there. This has to be a word because you can copy up to 64 kilobytes in one go. I mean, it will never be 64 kilobytes long in this case, but you can if you want to. Hey, Kelso. Losing your... Who was it who won shitloads last time? Was it Eldritch? Yeah, it was Eldritch. So there it goes. Okay, then the next... I can get rid of... Well, let's just put a space in there. So the next thing is the source address, followed by the destination address. Well, let's do the destination address first because we know what that's going to be, right? This is going to be our byte data on the rows. Now, this is something that we can make a table from because this isn't going to change between runs. So let's make a little table for this. So let's create a thing. Let's call it bitmap row addresses. Or let's just call it bitmap rows low and bitmap rows high. Now, bitmap starts at 10000. So we can set this, which is our sub bank value, to 1, and we'll just change the lower 2 bytes, so the low and the high. So this can remain as it is, and we're just going to change this one. So this is let me just put this in screen destination address, and we'll keep that at 00 here. So that's going to be the first row. But then we need to calculate what these are. So we need to fill to do that many view height. And we'll start at the beginning of the bitmap. We'll always assume that the view starts at the beginning of the bitmap. If we want it to be smaller, then we just shift the bitmap down the screen and change the height of it. But generally, it's going to be the same 128. So we need to fill this with a value, and this value is going to be, let's work out what our screen addresses would be. So it would be 10,000 plus, and this is quite simple, right? As I said before, with a screen layout like this, the strips of characters going down, every row is just 8 bytes ahead of the last one. So if you're starting on the very left-hand side, all you need to do is your row number times 8. So the first row will be at 1,000 or 10,000. Next one will be 10,008, 10,010, and so on and so on and so on. So nice and simple. This is our screen address, and we just want the lower byte of that. So we're going to take that, and then we're going to do the same with here, but with the upper byte. So now we have our bitmap screen address, and we're going to create a label for that here as well. So we're going to call this destination address. I could have just put I could put a label here, but I'm going to do it like this to stay consistent with these ones up here. Let's call it just dest address actually. So, and let's put that in this list here. We've got a raid. Old School Coder. Thank you very much for the raid, Old School Coder. Hope you're doing well. I forgot you stream on Wednesday. I always forget that. I don't often stream on Wednesday, so yeah. Anyway, cheers. Thank you for the raid. Hope you're doing well. What we Oh my god. What were you doing tonight then, John? What were you doing? Were you doing some more BBC stuff? I need to watch some of the BBC stuff because I my first kind of love of computers was on the BBC, so I'd really like to go and do some assembly language because I've never done assembly language on the BBC, which is a shame because it's got um, the best basic with built-in assembly, inline assembly. So I would love to go and do that at some point. I did do a lot of the basic, a hell of a lot of the basic. So, um, oh, it was C64. Okay, cool. What were you doing on the C64 then? Yeah, I need to see some of the BBC stuff. Definitely. Thing is, I've got a BBC. I've got a BBC Model B up there. I think I upgraded the RAM in it as well, but I just not had time to do anything with it, to be honest. Got a couple of electrons as well, so I got to say the new alert text really sticks out a lot better. So thank you for whoever suggested that last time. Thank you, Microman, for the resub. Smooth scrolling with screen and animating the characters on the screen. Okay, cool. Animating the characters in as in changing the character numbers on the fly, or do you mean kind of like updating the data within the characters? So like doing like parallax scrolling kind of effects by doing that. Thank you as well for the host prize, so and appreciated. Redefine the charts. Yeah, okay. There's a few sneaky tricks. Like one of the sneaky tricks that you can do is if you're scrolling the screen, then what you can do is you can keep a record of if you've got a character that animates, right? You can keep a record of those as the screen gets drawn. If it's a character that animates, you push it onto onto an animation stack, if you like, and then you have a record of the screen locations of all the characters that animate. And so what you can do then is if you scroll the screen again, you have to shift everything in that thing. You can shift. You don't have to shift it in raster time. You can kind of do it. You can do it wherever you want. It's not important because it's just a data structure, but you still need to shift the locations in there. And if it shifts outside of the screen area, you pop it off the stack, or well, it's not even a stack. It's like a uh, it's just a kind of registry of characters, and then you can when you do the animation, you can just look through this registry and go, these are the characters and these are the locations. So you don't have to think about anything. You just got a list of locations. You go to that location, change the character there. Really cool way of doing it. Something Doc does in Doc 2 actually. I definitely need to get back to that at some point, but I kind of tempted to do it on the Mega Drive. So anyway, let's get back to this. So thank you very much for the raid. Anyway, cheers. So that's our screen address. This will be filled in from this. We can do that right now, actually, quite easily. Unfortunately, the view height is going the wrong way here. So let's just change this to go the other way for now. We can reverse these loops if we need to at some point, but I think this is absolutely fine. The Mega65 is so fast, you'd be surprised how much it can actually do in a single frame. It's kind of insane how much it can do. Mega Drive Dock 2 confirmed. I'm really, really. The only thing that's holding me back on it, well, two things holding me back on it. Firstly, I'm not sure how I would do the time travel thing. Thanks, Dockster. Thanks for joining. Good luck with getting the Mega65 Nexus 7 board before the weekend. I'll keep my fingers crossed for you. Yeah, so one of the things is I'm not sure how to represent the time travel on the Mega Drive. it was kind of it was very simple to do on the C64. You had multicolor graphics, PET graphics. The Game Boy made sense. You had color, monochrome. So it kind of worked like that. With the Mega Drive, I'm not sure how you would do that, because even if you went from Mega Drive to, like, say, Master System, it wouldn't be a huge change. It wouldn't be enough of a change for it to feel like a massive kind of generational shift in graphics, if you like. The other option, of course, is going right back to, like, the SG-1000 or something like that, and doing that. I don't know, but yeah, yeah, exactly. So yeah, I need to have a think about how to do that. The other thing is, of course, is getting the graphics drawn, because obviously it's a bit of a step up once you move into 16-bit and you start having all these colors. It was a bit easier to do on the Game Boy because the screen is relatively small, so you can get away with kind of quite low quality art on it. Um, if you're willing to do it, then I'd be up for that, definitely. I mean, I need to learn the 68K first, but yeah, I could definitely do with somebody who's willing to help out with that, because I certainly don't have the skills to do that. Um, I have lots of kind of pre-drawn graphics for the C64 that could be used as a kind of base. I know what I want from all the levels. I've got it all mapped out exactly in my mind. Um, how it looked, like the order of the levels, what the kind of style of each of the levels are. The only thing I don't have is the enemies, because I was kind of basing the enemies on um I was basing the enemies on whatever I could draw at the time. So um but yeah, it's something we can look at when it comes to it. It's going to be next year before I do that anyway, because I want to focus all my effort into the Mega 65 and making the Mega 65 as successful as possible, and hopefully getting a decent library of games from both myself and from all the people that are entering these competitions, which I'm really grateful for as well. By the way, everybody that enters these, you're no, I mean, obviously, you're in with a chance of winning the these Mega 65 Nexus things as well. But more than that, what you're doing is you're helping to stabilize the code base, hoping to um, when I say code base, I mean kind of the FPGA core and the emulator. You're helping to raise awareness of the machine as well, because every time we do one of these competitions, it ends up in a video somewhere, either from myself, from the Mega 65 team. More people see that, what the machine is capable of. They can see that there is stuff being written for it. We're slowly building a developer community up, and that to me is the most important thing. Is getting the machine stable so that people can dip in and have a test of it. They can download the emulator, have a go, and see what it looks like, and get a feel for the machine. But that they can also have a library of stuff that they can look at, and a library of kind of information that they can find out, a library of knowledge. We're helping flesh out the manual as well. Every time we do something and we discover something new, it ends up into the manual. Um, this trying to make as much of the source code available as well. So yeah, it's all very very helpful. So I appreciate it a lot, and I realize that you can win prizes, but for me that's the minor thing on it. The big thing is the is getting the interest there. Okay, so we can set the destination address now, so that's quite easy. We just need to load uh bitmap rows low, comma x, and store that at not source direction, destination address +0, and bitmap rows high, and store that at address 1. Okay, cool. So this is actually filling in the destination address ahead of time, so that's good. um, then the final thing we need is the source address. So this is where it gets a little bit trickier, and this is where we need to actually sort out our let's spell it out completely. As soon as we're spelling it out completely up there, This is where we need our new data format, and that's what we're gonna. This is where we're gonna do some work here. So, what's the game with the BG? Guess the character. Yeah. So there's currently 544 backgrounds, and you can change the picture by typing BG and a name, and you have to kind of guess what the images might be. I've started creating series, and you can submit a series to me if you want a sequence of pictures, including. They just need to have a common theme, preferably around about 10. Um, it's really just a kind of really just kind of extra bit of fun for the stream, to give me a reason to have the green screen behind me as well. Up to 80 sprites for the Sega Mega Drive. Oh, bless. Do you know the funny thing is, I think as I start coding on the Mega Drive, I'm constantly going to thinking, I wish I had the power of the Mega 65, and that to me is amazing. That I'll be constantly wishing I had the power of the 8-bit machine to do the Mega Drive stuff. But there is stuff on the Mega Drive that I think I'm going to really enjoy. Unfortunately, I don't think 68K is going to be one of them, but it's going to be better than Z80. Anything's better than that. Right, more vodka. So we need the source address, and this is going to come from our data structure. So this is where I'm going to define how this data structure is going to work. Yeah, it's insane. The things like the way the DMA works. I mean, obviously we've got the advantage of modern kind of FPGA, so and kind of hindsight, which means we can look at these things and make things work exactly how we want them to work. But I think the kind of architectural design that's gone into the Mega 65 is really, really clever. The raster rewrite buffer is genius. I honestly believe it's genius. And I think that the way the DMA works and the enhancements that have been made to it. So the DMA was always there, even in the original Commodore 65. That was there. But what Paul and the team have done is they've enhanced it. They've added loads of extra modes into it without breaking them. So genius and a pain in the ass. But see, I like that. I like the fact that it's a pain in the ass because it makes it Commodore. It wouldn't be a Commodore machine if it wasn't a pain in the ass. So I like that. As I said this a few times before, I think the raster rewrite buffer is the multiplexer of the Mega 65. So multiplexers were for kind of beginner coders and even to a certain extent intermediate coders. Multiplexers could be difficult to get right and efficient on the Commodore 64. So they were always a good multiplex was always kind of a holy grail of code on the Mega 64 on the Commodore 64. And I think the raster rewrite buffer is going to provide that kind of holy grail for the Mega 65 as well. I think the code I've got for the raster rewrite buffer is okay, but I think there will be people who manage to get even more out of it and find ways to do crazy stuff with it that we haven't even thought about doing yet. So that's where I think between that and the DMA, I think that is the new kind of frontier of the Mega 65. Okay, where's my smoke? Here it is. Okay, destination address. Okay, so I'm going to define a few more things here. What I'm going to do is I'm going to use the area just after the bitmap data for the. I know, actually, I'll tell you what I'm going to do. No, I will use the area after this. Okay, so this is going to be uh, our buffer data. And what do I mean by buffer data? Well, I mean the data like this. So this it's just going to be a strip of pixels. These gaps won't be at the end. So actually, what it will look like is more like this. If you were to be, oops, if you were to be accurate about it, with each color kind of bleeding into the next one. So it's just a stream of data like that. But what I'm going to do is I'm going to insert at the beginning of each one of these, I'm going to insert 2 bytes, which is the length of this line. So these white blocks represent the bytes that say the length of the line. So that means we can sequentially go through this very easily. We can set a counter to the beginning, a vector that points to the beginning. We can read the first 2 bytes, and we know how long the line is then. So then we insert that data into here, and we use the length to work out what the stepper is, what this value is here. So that will give us a source address, and it will give us a length as well. And that way we've got a linear buffer of data which we can then copy to the screen. So yeah, the Swift multiplex is pretty good. In fact, I think the one that I use in Parasol Stars, the sort that I use anyway, is based on the Swift. It's the sort that is the key thing. If you can get the sort done well, then the rest kind of falls into place. So I use a modified Swift sort, which I got from Cadaver's site, I think. But then what I do is I've modified it to also generate raster positions as well. And those raster positions allow me to save a few cycles allow me to get tighter sprites together by automatically working out where the next line is going to be, so you don't have to do any comparisons or anything. You just has a list of where the rasters should be. Isn't data already on another series? Yeah. So the way the series works is you can have I just noticed there's a bit of a weird kind of glitch in the display of series. It has a square bracket on one end and not on the other. You can set any image to belong to a series, even if you've already seen it, even if it wasn't in a series before. So if data was already available as an image, he can be added to a series quite easily. However, he can only be added to one series. If he's added to multiple series, there may be some bugs with the way that works. I'll have to check how that happens, but yeah, anyway. Okay, so yeah, that's how I'm going to do the data. So what I need to do is I need to create a location for this. So this is going to be basically the location of bitmap data plus whatever the last thing is. So what have we got? We've got 40 columns, 16 rows, and each one is 64 bytes. So this, I'm going to put it in square brackets here. This is the address of the last byte in memory. So the last byte in memory of the bitmap. So that's going to be a section. I'm going to just check how big that is because it needs to be big enough to hold this buffer. It should be big enough, I think. But let me do this in programmer mode. So 40 times 16 times 64 gives A000. So that means we've got 6000 bytes. Oh yeah, so 24,000 bytes. So that's plenty. But that's where our buffer data is going to be. So the data is always going to be stored here. And we'll need to create some dummy data to put in there in a minute. But actually, let's put that dummy data in now. Okay, so let's create a little function down here, which I'm going to call. I'll put it right at the bottom here. So fill buffer dummy. Okay, and this can be a DMA as well. This just needs to basically copy very quickly DMA job, yes, job, and create dummy data here, like so. Oh wow, Deft, thank you very much. My God, you're all absolutely insane. I will report back how many bits you guys you have donated tonight, but it's quite a lot. I mean, it's got to be like 10,000 at least. You guys have been insane. Thank you very much for the bits, Deft. The call ended. Cool. I've kind of gone the long way around this, but I really wanted to explain everything that I'm doing. Um, I'm sure it said 11,400 after the first hype train. Wow, yeah. Well, it's good because I mean, this month was a pretty good month payout. It wasn't enough to buy two of these, but it's definitely enough to buy one with a nice kind of margin for postage and stuff. So that's kind of nice. It's a little bit of breathing room this month. But I think next month, because it runs from mid month to mid month, I think next month we may be very close to two. But what I might do, because I know not everybody's interested in owning one of these anyway, so what I may do on the next month is do just a single one of these giveaway. Actually, that's rattling. Why is that rattling? Okay, I need to check that. It doesn't seem to be down hard enough. And then give away maybe give away one of these as well next month. So there may be a Raspberry Pi giveaway, which I'll do the standard way where I do the when I do the ticket giveaways. So um yeah. So we want to, yeah. But yeah, I may give away a Pi 400 next month as well, or maybe even two, depending on how we've done well. So bugger, I've won both of them. You have won both of them. Well, you won one, and your missus won one, um, which was kind of funny. She got an easy Christmas present for you there. But thank you for the bits again, Deft. Um, she gave it to me because she loves me, or she felt sorry for you. Okay, so we want to copy this job. So the thing we need to do here is we need to know how long this is. So I'm actually just gonna now do this. This is not going to be how it works. This is just a demo. Demo. Oh yeah, I've already so I'm getting a couple of copies of Doc sent to me. I'm going to give one to Sean, my son. I'm going to keep one for myself, and I'm going to give the third one away in a competition. So don't have to worry about an extra copy. I'm just going to give the third one away in a competition anyway. Um, any news on the Doc digital download? I don't know. I need to speak to Zappy about how we're going to do this because normally I just put my games onto itch. But I don't want to do that, at least not for the first kind of few months, to give the physical sales a chance to sell, but also to give Bitmapsoft the opportunity to do it through their systems anyway first. Uh, this time next year, or like January next year, I will just put it on itch at whatever price, just so that it's there and more people can see it. But I want to give Bitmapsoft the kind of, because they put so much time and effort into publishing Doc for me, and creating the manual, creating the box art, and these beautiful Game Boys. They did so much lovely work that I don't want to list it on itch. So like Luma, I listed on it straight away. Pretty much, that was just how it worked. There was a digital version of it on it, but I don't want to do this with Doc. I want to let Bitmapsoft run this at least for the first kind of 12 months or so before I just list it on it. So anyway, okay. So dummy data that goes in there. Okay, so the dummy data is just going to be some stuff that we're going to copy into our bitmap buffer data up here. So this is the job that we're going to do. We need a DMA header in here. We need a DMA copy job. This needs a. So I can never remember this. I wrote this and I still don't remember how it works. So. But yeah, regarding the digital download, I don't know when the best time for that to come out is. It needs to be a little time after the kind of live date to give the physical sales a chance to sell. They've done pretty well though, to be honest. DMA copy job. There we go. Source, destination, length, chain it backwards. Okay, so source is dummy data. Destination is buffer data. Length is dummy data minus dummy data. Chain is no, backwards is no. Okay, cool. So this is just a very simple job that's just gonna just fill the buffer data with some stuff. So now we need to create that. So what we're going to do is we're going to create a list. We'll just go we'll go backwards, and basically we need to fill in an address. No, sorry, a length, and then some data for that. So let's work out what a length would be. So our length, let's make this. So it needs to be so. If you look at the curve for this, let me just bring up a graph curve thing. Equation graph is usually a good one. Equation graph. There we go. So the curve for this is going to be something like is it 1 over y squared? No, x equals 1 over y. There you go. But it would be more like no. Oh yeah, so well, it would be kind of backwards like that, but you can imagine it upside down, right? So basically, this is the far plane, and this is the length of a line on the far plane, and then as you approach the near plane, this is the length of the scan lines that we're taking from the texture. So this is kind of the curve that it's going to look like. It's not a straight line, so we kind of have to make that kind of the same here, really. So the easiest way I think to do this is going to be if we do I divided by 127, that's going to give us a length between 0 and 1 roughly, right? Let's do I plus 1 here. I just want this to be accurate in terms of how the curve would look. And then actually we just did this upside down, this would probably work. So if we did 127 over a number, okay, so it'd be from 0. Just take a quick look at that again. So if we did this the other way around, no, see that's no, so it'd be 127 divided by y. Let's make that smaller so we can see the curve. Yeah, okay. All right, so yeah, that's what that's doing. So that's going to run from 1 in the this end at the high end. It's going to be no, that's going to be wrong, isn't it? So 127 divided by 127 would be 1. Let's just go this way. 127, so let's go 1 I. So I'm just trying to get this dummy data. This dummy data needs to be relatively accurate. So sorry, let me just answer this. Okay. So this would be yeah, I'm going to avoid the divide by 0. So I want the length to be biggest when it's at that end. So yeah, it would be 128 divided by I plus 1. There we go. So that's going to create a line that's 128 long at that end, and then slowly getting smaller. Yeah, all right. And then let's times this by 4 or something. And then that's just going to make sure that we've got a line that's really big at one end and then really small at the other end. Let's do by 3, actually. That makes it more sensible. So it's 384 as the maximum length here, roughly. Okay, cool. That's fine. All right. So then what we need to do is we need to store this length as some data. So we're going to store. So this is our length header. And this will be the lower byte of length and then the higher byte of length. So this is just literally just dummy data. And then we're going to fill length with, let's say, mod I15 plus 1. So that's just going to create a copy of the colors, basically. So this is going to be all the colors in the palette except for black. It's going to ignore black, and it's just going to repeat. So the lines are just going to repeat all the way along. But we should see an effect as it comes down the screen. So we should see some weird kind of lines and stuff as it works. But that should be enough. So this is going to give us 128 lines of decreasing size. So kind of like this, with 2 byte length header, and then a length of bytes, which is just going to be all the colors repeat, all the colors in the palette repeating. Yeah, okay. Oh, you still got 2 more of those to go. Who did this one? This was Quadrasul, wasn't it? I think this is one of the trickiest. It's definitely one of the trickiest series. So anyway, there we go. And then what I want to do is I just want to print out the size of that. So I just want to make sure that that is kind of within acceptable limits. We know that the limit is 24,000 bytes. So let's see what the dummy data size is. This is why I wanted to do a fairly accurate kind of size. Dummy data size equals, and then you can use 2 hex string. So if you haven't used this before, this is a function that exists in GigAssembly that just allows you to turn a number into a hex string instead. It just makes it easier for me to look at because I'm looking for 6,000 being the limit here. So if this is way less than 6,000, then I'm happy with that. Oops, plus the text string. There we go. Okay, we've got an unknown symbol here, 8 times I. Okay, I'll come to that in a second. Did it print anything? No, it didn't. All right, I need to go and fix that. So that's because this address here needs to be starting at 000 like that. And our sub bank here is also going to be 1 because that's where our bitmap buffer is up here. Bitmap data and buffer data here. In fact, what we can do is just to make sure that these are exactly right, is do this times shifted 16, and we'll still create 1, but it's worth doing that just so it's obvious that that's where it ties to. And then if we do move things around, they'll work. Okay, data size ATS, so it's not even using a 4 kilobyte block basically, so that's pretty good. Okay, so that's our dummy data. Let's make sure that that's actually called at the beginning. So we'll just call that here. So we'll probably be doing quite a lot of dummy data as we go through this, but this is the bit that I'm most interested in at the moment. So that's going to fill that dummy data up there. What I want to do very quickly is just run this and then just go and have a quick look at that and make sure that this kind of matches the format that we'd expect. So let's open up this, which is M65 Connect. This is going to allow us to read these values in memory. So if we're going to have a look at M18000, we should see that we've got some data in here. And our data is saying that our size is 180, which is 128 384, which indeed is correct. 3 times 128, that's exactly right. So that means if we look from here to 182, we should see the next one. So we can see that now the numbers are repeating. In fact, you can kind of see that in the, let me just move it over so you get that. You can kind of see the pattern in the numbers here as they're repeating the colors as we go along. Let's go all the way up to the next block. So we look at 182. We can see that, yes, indeed, we move on to the next section. We've got a new section here. It's now 192 long. So now if we have a look at, what's that going to be, 44 on the next one, 18244. We should see the next one, 244. There we go. Yeah, so this is exactly right. The data is kind of exactly what we'd expect, and the data runs all the way up to 1A8EF. So let's have a look at 1A800 and see if we can look at all the memory here and see what's going on. So yeah, as we get towards the end, this is the last byte. This is where the actual end is. You can see here that the previous was just 3 in size. It has a, oops, damn it. It has a header that was 3. So this looks good. This is working exactly what we'd expect, basically. Okay. So with that in mind, we can now go ahead and fill in the rest of the data in here, because now we've got some dummy data. So let's, when we copy the buffer, we need to actually do some dummy data stuff. So let's create where we don't need that one. Map vector we don't need. Screen vector I think we do need. Let me just check that that's actually been used. It's probably not been used actually. All right, we don't need it yet. Cool. In that case, let's create a fresh one in here. Let's create, yeah, I thought it was like that. I'm just trying to remember the format that I was set up in. Let's just call it buffer vector, I think. And we're going to initialize this with a D word, because we're going to use actually, is it going to use a D? Yes, it is. We're going to use Z index to look up here. Okay, so in here we also need reset buffer vector, which is the first thing we're going to call up here. The job of this is really, really simple. It's just going to take the buffer vector and store it into the locations. Now, this is always going to be 0 on the last one, because we're never going to be using the upper area of RAM for this buffer. This is always going to be in the fast RAM. But the rest of these can be adjusted accordingly. So that's going to get the upper byte. But we do need to add that with FF just in case there is another byte up there. There shouldn't be, but I like to do that anyway, just so it's implicit exactly what we're doing. Explicit, sorry, not implicit. Oh, Anton, thank you very much for the bits. Welcome. How are you doing? Well. God, I'm going through this vodka really fast. This vodka is delicious. It's my favorite vodka. I'd never had it before. I'd had Absolute before, but I'd never had the flavored stuff before. And this is really nice, like crazy, crazy good. Like I had it in the I had it in the freezer, and it was so nice when it's ice cold. Oh god, the soda down there. Anyway, cheers, Anton. Thank you for the bits. It's so good. This is well, this is raspberry and lime, so this is very similar. So, um, what have you been doing, Anton? You've been destroying satellites. We need to harness the power of satellites to do Mega65 stuff somehow. I don't know how, but it needs to happen. Okay, so yeah, this is just going to set up the vectors. And this is just going to reset it. So we need to do this whenever we start copying the buffer. We need to reset. We need to point back to the beginning, and then basically we can load Z. Well, actually, we'll do it here. So the other value we need to fill in is the source address. And the source address is a pretty easy one to grab, right? So okay, so we need to load. We need to get the length, right? So we need to load the accumulator with. Oh, hang on, it's that, isn't it? Yeah. Oh. Make the text yeah. Laser beam drawing like, oh my god, I feel really drunk. Wow, really drunk, and I'm doing maths. This is not good. I'll be fine. It's fine. I'm feeling very drunk though. I've had quite a lot of vodka. I've had like half a bottle tonight. I've got work tomorrow as well. Okay, so I'm going to load a buffer vector, comma z. Z needs to be 0 at this point, and this is our length LSB, and then we need to increase Z, and we need to store that at length MSB, and then the source address is buffer vector plus 2, right? So the easiest way to do this is going to be to take the current address, add 2, and store it in source address directly. So we're going to take buffer vector plus 0, clear carry bit, add 0, 2, and we're going to store that in source address plus 0. And then we obviously have to do the same with buffer address plus, plus 1, just in case it's overflowed into the next section. And there we go. That set our source address up. Now, our length is here, and that's where the reason I've created these two is these are going to be self-mod values here. And basically, we need to know what our stepper is. So if our line is 640 long and our screen is 320 wide, then our stepper would be 2.0, right? Or 2.0 like that, because we're using fixed point, right? If likewise, if our value was 160, so if our length here was 160, our screen is 320, so our stepper would be 0, 1 to 8. So the easiest way to do this is with the hardware math unit, and that's what we're going to use here. So first of all, we're going to load the length into the A part of that, and actually let me bring it up in the manual. Math unit. So we're going to use this hardware accelerated math unit. It's really, really handy and very, very quick to use, but it's perfect for doing these sort of things. Basically, you have some A and B values. These are 32-bit values. You fill in the values for A and B, and once you've filled in the values of A and B, then the 64-bit values for multiply, add, and divide out are automatically calculated. Oh, how are you missing that one? How were you missing that one? That's crazy. That's one of the early series. So when I did the alkali metals, that's what the series is. But yeah, that is actually what that is. That is a cesium clock here. So that tube that you can see there has a cesium isotope in it, which as it decays, it picks up the rate of decay and it uses that as a kind of source of kind of time tick. We're used to seeing quartz crystals because quartz crystals tend to oscillate. They do oscillate when you pass electricity through them at an exact frequency. This is just using a similar kind of technique where you're looking at the frequency of something happening. It's just that this is even more precise. So cesium clocks are very, very precise indeed. I believe they use cesium clocks in satellites. So maybe Anton can answer that actually, but I'm pretty sure they use them in satellites like GPS and stuff so that they can time things properly. And they have to actually account for relativity as well. They have to actually account for the fact that because it's orbiting the Earth at crazy speeds, that the time will actually slow down slightly. So their clock has to be very precise and it has to be adjusted so that it actually runs slightly faster or slower. I can't remember which way it is, but it has to run slightly different to a clock that we have on Earth to account for the bending of space time as you approach faster speeds. It's not much, but it is enough that it has to actually be accounted for. Otherwise, your GPS just simply wouldn't work. So, anyway, enough of that. I like that sort of stuff. Always find that super interesting. Okay, so we need to work out the source fraction. So what we're going to do, we're going to add a new function in here. Not a function, a macro. I'm going to use the prefix math for these. And we're going to do, this is a division, right? So as I showed in here, we need to do a division. I don't remember, that was fun. A nerd. I love, I honestly, I watch that sort of stuff all the time. Yeah. Especially going light speed, you know, embarrassing clocks. Yeah. Yeah. So let's do math divide, right? So what this needs to do is this needs to take the value that we pass into in, uh, and this can either be, don't know how to do this. If in is null, no, I need to think about how to do this. We need to pass this value in, right? Yeah, actually, let's do like that. So if in equals null, then we're going to store accumulator in. So let's do this as a, let's do these in sections. So we're going to do a 16-bit divide here. So this is a 16-bit numerator and denominator, or divisor, however you want to call it. Yeah, physics is awesome. Physics is great. I watch so many YouTube videos just around physics. It's crazy. Between what's his face? Tom Scott, is it? I think his name is. Tom Scott is one guy. Veritasium is another one. Who else? The physics girl is another one as well. I like Professor Dave. There's loads. There's loads of really really good physics channels as well. Very good to watch. Professor Dave is a particular favorite of mine when he has a go at the flat earthers. It really cracks me up, that stuff. Okay, so what we're going to do is we're going to fill these math units. So we're just going to use a 16-bit. So the easiest way to think about the math unit when you're doing the divide is if you pass in a 16-bit value, or well, let's treat it as the full 32-bit, right? So these are the ins, right? You've got 32-bit values. So you pass this in, then the first 4 bits are going to be your of the same kind of exponent as these values. So if you pass in 1 divided by 2, then you're setting 1 in here, you're setting 2 in here, and the rest is 0. Then that means your output, this is going to be your integers. The first 4 is going to be your integers, and these are going to be your decimals in here. So that's how we're going to treat this. We're going to treat 16-bit values in passing in these two here and these two here, and these two will be set to 0. So let's take a look at that from the point of view of this. So we're going to store accumulator as the LSB, X as the MSB, and we're going to store that in D770. Store X in D771. Otherwise, what we're going to do is we're going to take the value that this is pointing to. So we're going to load the accumulator with in plus 0, store this at D770. And that gives us 2 ways of passing information in here, like so. Or we could set them up ahead of time in here as well. Actually, let's do it without the macro first. Let's show you it without the macro first. Probably the easiest way. All right, so we're going to set the LSB up. So this is D770, and this is the top half. So this is A. This is this bit here. So we're going to store that in D770 like that. And I'm going to put a little mark here to say multiplier multi A LSB or byte 0. There we go. Might as well make this as efficient as possible, right? And then this is the MSB, so this is byte 1. So now we've got byte 1 and byte 2 set up, byte 0 and byte 1 set up, and then we just need to make sure that the other ones are 0. If we don't set these to 0, and they've previously been set somewhere else, I believe they default to 0, but if they've been set somewhere else, then our output is obviously going to be wrong. So, oh my God, you guys are really catching up with the things. So, okay. So this is our DMA values for sorry, not the DMA values, the math unit values for this bit, the top half. So let's put that in here. So length, so fraction step equals length over screen width or view width. Length is already set above. So we just need to set the view width now. So the view width is going to go in the next 4 down. So if you look in the math unit, you can see we've got multi in A here. Multi in B starts at D774. So we're looking to store the length at D774 and D775 with a 0. D776, D777. I'm going to copy these over here so we can see what those are here. That's still byte 0. That's byte 1. But this is the multi-A, math multi-B, right? Oh, what kind of file do you use to make a small hole bigger? What? Well, that makes no sense at all. That is a terrible, terrible, terrible joke. It's good fun watching Mike Boulifant try to do laboratory random bits of junk and open fires. Oh, I really like the Royal Academy of Science chemistry lectures as well. They're good fun. Some of them are a bit dated and that, but they're still very good fun to watch. You learn some pretty amazing shit as well. That's the thing I really like about it, is that like until YouTube came along, you had to go down to a library and do stuff. Um, the YouTube has made it very easy to find these things. So yeah. Okay, cool. So now we need to set the well, that joke I'm out. Don't go monsters. I don't even get it anyway. It doesn't even make any sense to me. Or is it just really oh, actually I think I do get it. That's terrible. Okay. Yeah, that's quite bad actually. That's quite bad. Yeah, let's keep it decent. Okay. It took me a while to get it. I get it now, but it's yeah, it's not a great one. Okay, so now we just need the screen length. So this is going to come from we need the lower byte of M7 view width, and this would be view the upper byte. Now, one thing about the math unit is it does have lots and lots of units. So I don't know if they're all active. I'm just using the default one at the moment. But if you take a look at if you take a look at this, there's lots of in units, and what you can do is you can set these up so that you can use these to kind of you can set some kind of how many there are, the 15 16 different in units, so you can set 16 different values, and you can have different out values that just use combinations of those. So for instance, in this case, our view width is never going to change. This is a constant, so we could set a math unit up which always divides by 320, so we never have to do this every frame, which is a really useful useful system that kind of avoids having to repeat things. So yeah, we just need to keep it decent. It was yeah, don't worry about it. Don't worry about it. Okay. Okay, so that's our division. So now with these two values filled in, with this value filled in here and this value filled in, our division should return the value that we need. Now, the only thing we do need to do is we need to waste some cycles. The reason being is because the division takes a little bit of time to get its precision. I'm not sure exactly how much you need to waste here, but I found that if I just load the border color twice, that's usually enough. Um, but at this point now, we have a value that's now stored in. Let me find the value. It's stored in here, D768 to D76F. Now, our integer is going to be here, and our decimals are going to be here. So we need to look at this from the point of view of the slope, not the slope, the stepper. Now the stepper has an integer component here and a fractional component. So we just need two of these values. So we need the integer, which is going to be this one here, D76C, and the fraction, which is going to be D76B. So let's do that. D76B is our fraction. I'm going to store that at source fraction. Oops. D76C, which is going to be our integer. Okay, so now we've got the source integer and fraction in place. They should be able to run this job. That's everything we need to run this job. Let's put this down here. So let's just double check that now. So we're grabbing the data of the buffer here. Those values are stored in D770 and D771. Those values don't change, I believe. So I think we can just read those back out again, and we'll need them in a second here. Where we're going to advance buffer pointer. So what we're going to do here is we're going to take buffer vector plus 0. We're going to add the contents of D770 because that is our LSB. That is our low byte of the length, basically. Right, so we do need to clear the carry bit here. And this means that once we've done this addition, when we get round to the next iteration of the loop, the next thing that's going to be read is the length again. So okay, cool. Let me just check something quickly. There we go. Cool. So this should, in theory, copy everything from that buffer to the screen. So let's give that a run and see how that works. So copy buffer DMA in M7 buffer. Okay, so here's our loop. So let's set a loop up here. Let's call it main loop. Let's jump to main loop minus. Let's jump to subroutine copy buffer in M7 buffer. Okay, but we want to do that once we've reached a certain point. So I'm going to actually put the raster kind of at the top of the screen somewhere, just because it's a little bit easier to see instead of it being off in the border somewhere. So, and again, we're going to do 2 of these because of the speed of the Mega65. Probably don't need to do 2 because of the length of this operation. But hopefully, what we should see now is it's going to look like junk, but we should see some stuff fill that screen at the bottom. If all has gone well. Well, it's running, so that's good. We'll get an idea of how long this operation takes. Okay, so we're seeing some stuff, but it's all printing on the same line. So let me just bring that up on the main screen. It looks like it's just 1 row of pixels here. That's not a bad. It's not bad actually. Let me put it on my TV because I can see it on my TV a little bit better. So input HTML 4, please. Okay, so it's actually printing 2 lines of colors. That's interesting. Okay, so let's take a quick look again. Okay. So, oh no, we are advancing down the screen. Okay, so let's make some changes to this to make sure that we're actually filling the screen properly. So let's forgo some of these for a second, and let's change this to. What is the fill jar? I think it's 01. Let me change it to a fill jar. It's 03. Okay. Okay, so let me change this to 03. So this will fill. Source address doesn't matter. Let's just see what happens here. Okay, so we're just getting. Oh well, we are actually getting black in the second half, so it is filling it with something. Let's change this to red here. Just turn off the source address right in here. So that source address is here. So let's just turn that off for a second because we're using fill. I just want to make sure if this all goes red, then this is good. Okay, so it's definitely moving down the screen. It's filling with each individual color. Let's leave that out for a second. Let's change source address. Okay, so let's just after that source address in this one here, I'm going to put load accumulator transfer. What was it? X, yeah, X the accumulator and with 0F. Okay, so this should show bands of color moving down the screen. That's perfect. They're following the pattern of colors, so that's good. So we know that this is working as it moves down the screen. It just seems to be source address that's not quite right. Okay, so let's go back to our source data in here and just change this a little bit. So we're going to change this to have this value up here. So we're going to take, let's copy that line so I don't lose it. Just comment it out. So I want each line to be a new color. Don't know why I've suddenly done it like that. There we go. So this is going to be a fairly slow process getting this to work, but it is going to be a fun process to say the least. Okay, so something is not picking the buffer addresses up right or something. I'm not entirely sure what it is. Let's take a quick look. I can see one problem here. Okay, so oh no, this should be right. Buffer vector source address. Yeah, that should be fine. Okay. Destination address. So our length should always be. Oh, where's our length gone actually? Here. That should be 0. Okay. It's only ever drawing 2 lines though. That's the fucking weird thing here. Whereas the destination is working, but it looks like we're not doing enough in terms of the source. Could be these values that are wrong as well. Let's try not changing these at all. Or let's just leave them on 0, 1 to 8. So let's not change the fractions at all. Let's leave those alone. Just trying to work out exactly what's going on first. So booby alert, Sean. That's fine. Okay, that's interesting. So that is actually copying at half the width, but it seems to stop after the second line for some reason. Which makes me wonder if the destination address is correct. Okay, let's not do the advance. I think maybe this is wrong. So let's not advance the pointer at all. Okay, cool. So it's to do with the advance that we're advancing incorrectly here. That's fine. We jump back to here, which loads Z again. Buffer vector points to a new location. Okay. So in that case, we can't trust the values in here to be our length. Even though we're setting them here, we can't trust them to be our length. So let's set length LSB MSB. See if that makes any difference. Uh, this series is making you Google some weird bands. Did you work out what the thing was, by the way? I can think of at least one you haven't got. 4164. Yeah, 4164 was what was it? That was the 8K. Yeah, the 8K chip. Yeah. So it was 64. Well, yeah, it's the 1 byte chip. So you're just using Redeem now. You're cheating. There's only 41. Where is beef? Oh, so I use beef because so I'm using immediate mode here. You can see that I'm using immediate mode there, but I use beef as an indicator to say that it's a self-modified value. So anytime I see beef, I know it's a modified value, self-modified value. So what this is actually doing in terms of the assembler is just that basically. It ignores the upper byte, but it's a really good way for me to look at code and go, ah, yeah, that's self-modified code. But however, this has not made a difference. It's actually doing exactly the same thing. So I don't believe that is actually correct. And the reason I don't think this is correct is because actually the length needs to be +2. That's the problem here. Because we need to include the header, right? So the length actually needs to be, the length is correct here. That's fine. But we actually need to advance the buffer vector by 2 here. So actually I'm actually gonna store this as we go along. And then it will be correct. So if I do that there and there, that should be correct. Or because I've got the source address set up, what I can do to save bytes and cycles is source address like that. So there we go. That should be right now. DEFCON 201 live. Thank you very much for the host. Very much appreciated. Why is that not running? Something is not running. What have I done wrong? Oh, because now I've got this and I don't need this anymore. There we go. I forgot about that. Yay, there we go. So that's kind of what we would expect. It looks about right. So that weird curve is because of that, the way actually, it's probably not quite right. I would expect to see some of these colors stretched, but we're not seeing that. So, oh, I know why, because we turned the source fractions off. So I think if I turn the fractions back on again, it should probably look correct. There we go. Perfect. So what we're seeing there, let me go back to the I and fill length I and okay, let's do that one. Get rid of the transparency bits. There we go. Perfect. So it looks a bit weird, but that's because what you're seeing now is you're seeing these lines stretched out to fill the screen. Now it is taking quite a bit of time to do that. Actually, that is quite a large amount of time. So I may look at finding a way to optimize that later. For now, I don't really care. As long as I can fit this all within one frame, I don't really care because the Mega65 is so fast. If I take 3/4 of a frame to draw this, then it's a quarter of a frame doesn't seem like a lot, but it's still plenty of time to do all the game logic and everything else. This is the hard work. This is the difficult work. So what we're seeing here is we're seeing increasingly smaller lines, that are all the colors that are just pixels of the same 1 pixel of each color in the palette of the C64, with the exception of black, which is transparent, drawn from the very back to the front of the screen. And what's happening is as we go down the screen, because the lines are decreasing in length, they're being stretched across the screen. So you'll see at the very top, the pixels, the blocks of color are 1 pixel wide. But as we move down the screen, the blocks of color get wider and wider and wider and wider. Um, we need a commentary of, of River's holiday through the diesel deck and his telegraph pole collection. Yeah. I don't know how I can focus. You try streaming this week. Alcohol. That's how. But yeah, you can see there it's working fine, and you can see what I mean about slices of the track that we take. So when we look at the slices, um, when we look at the slices here, as we get closer and closer to the screen, those slices get wider and wider in terms of how many rows of the screen they fill up, which is why at the very top of the screen, the pixels, the colors are 1 pixel high. But as you approach the bottom of the screen, they become many, many, many pixels high. And the reason for that is because as you get to the bottom of the screen, these lines here at the bottom of the thing are so close together. Even if I zoom right in, you're not going to see it. They're they're all reading the same pixel. So the bottom like 20 lines or so here are all reading the very same pixel. So what we see on the screen is we see the same stretched pixel copied several times. Again, this could be an optimization. We could do a calculation which works out, actually you are using exactly the same pixels here. Just display what you displayed before. However, that's probably not going to work perfectly because you have to account for different slopes, and different slopes are going to have different like widths of kind of texture data before they go. But this is the basics basically of the buffer copy. So what we have now is we have the copy from the data that we extract from this map linearly somewhere else into memory to something that we can display on screen. So the next step is to take this a step further, and go with actually, can we actually, it doesn't really matter if I center this or not. You can see the 3D effect kind of happening if you look at the way this is drawn. You can definitely see the 3D effect happening. It just looks weird because we're all left aligned here. So at the moment when we're taking data, all our data is left aligned at the moment over here. So it'd be the equivalent of taking this, drawing a line down the middle, and extending this out this way instead. Um, but we are one step away from it. So I'm glad we got that bit sorted out. That's um, it's taken a few more raster lines than I would have liked, but I'm wondering if that's to do with not doing and not using chains, but instead kind of doing this every frame. So let's see if we can optimize it a little bit. So let's take a look at what we're actually doing. Okay, so we're using these math units, right? So let's create an init in here. Let's see if we can't use the other math units to do this. So let's configure math units. So instead of setting all the values every frame, we're going to leave this one in place because we know this one's never going to change. We're going to leave the 0 here because that's never going to change. We're only ever going to use these values here. The line's never going to be big enough to stretch into a third byte here, because that would mean that the line was 65,000 pixels long, and it's never going to be that long. So let's try and set these things up. Okay, so so this is a pseudo 3D effect. Yeah. So as I say, you can use. I mean, at the moment, what we're doing here now is just basically, as I say, I'm kind of approaching this backwards. I know how this is going to work. We're going to take the data from this map, and we're going to store it in memory so it looks a bit like this, with each color being a new line on the screen. And then that data gets transferred to the screen in that pattern, with each line being scaled to fill the full width of the screen. Hopefully what we can do now actually is we can change the width of the screen, and it should adjust automatically. So if I change the width of the screen, we should see the raster bar change in size, right? So if I go in here and I change the width to half the size, there you go. So it's ignoring one half, and what it's done now is it's squashed everything. So it hasn't truncated, it hasn't cropped anything. You'll notice that the white, red, and cyan at the bottom. Notice how the cyan is about half the size of the red on the bottom row. If I put that back to 320, it will still be about half the size. It's not truncating anything. It's not cropping. It's just squashing the screen in. And you can see, there you go. So what you could actually do with this is you could use this to do multiplayer, right? So you could do two players by setting the view width to 160 and having one bitmap on one side and one bitmap on the other side with two different views of the track. So now you could set a split down the middle, and you've got left and right players quite easily. I'm not going to do that now, but it should be an easy task to adapt this to do that. It's certainly something I'd like to do, and you can see from the DMA, it's probably only it's just over half of the previous one. I'd say it's probably about 60% rather than 50%. So you do add a little bit of overhead for adding a second player, maybe about 20% overhead, um, but not a huge amount, I wouldn't think. So it's going to be very easy to do this. Likewise, we can change the view height as well, which will also change. So if I did 64, we could also do horizontal split instead. This is not going to be quite right because the bitmap is going to be halfway up the screen, and now because the view height is different, it actually changes the where the track stops drawing. You can see that if I do that in here, if I change the view height in here, you can see how it changes things quite significantly. So, but we can definitely play around with these values and shift things around, and find ways to do one or two players quite easily. You could even do four players if you really wanted to. I mean, you could do 160, 64 like that, and you would have a player in the corner. So yeah, that's the raster time used. So you can see there, if you imagine that shifted down so it meets the bottom, and then duplicated in all four corners, you can see the raster time isn't that bad. And you could technically have four players. I mean, obviously, you don't really have an easy way of doing four-player control, but it's possible. One thing that the Mega65 does have is an Ethernet port as well, so potentially this could be online multiplayer as well. I'd need to take a look at that. It's definitely a possibility. But let's see if we can optimize this math routine a little bit. So let's start with I got myself. Sorry, I was reading things. I think a few of you were a bit too early with the backgrounds. Okay, so we've got math in 0, math in 1. So what we'll do is we'll use 0 and 1. So we're going to use D780, D784. Okay, so let's set these up. So this is the which one is it? What are we doing here? This is the source fraction integer. We're using math unit 0 over math unit 1. So that's at D. So first of all, we need to reset these. Let's start by resetting them. We can fill the values in. So this is a D780. 1, 2, 3, 4, 5, 6, 7. I did too many. So it means we're going to have to initialize this buffer before we go into it. But initializing it should allow us to a little bit kind of more flexibility with the math units, in that we won't have to keep replacing values in the math units. We can just use this one specifically for this task. So I need to go and find here. Okay, so unit 0 in unit 0. Okay, I need to quickly read a little bit about this. Hang on. Set which of the 16 is input A for math function unit 10. Okay. Okay, so unit 0 in unit 0 in B. So I'm thinking what that means is okay, so there is a value in here, D7C0. So we're going to put 0 in it. And what this is going to do, this is set unit 0 equals multi-0 so A equals multi-0 and B equals multi-1. So that means we need to set A is on the left-hand side on bits. Okay, and so it's the MSB, which is B. Okay, so that would be 1, 0. Do it like that. There we go. Okay, so now if we use multi 0 and multi 1, the output of those values will appear in unit 0 out. Now, is that a multiplier or is that a divider? No. Oh, maybe this only works for multiplication. Well, that's a very good point. I need to figure that out. Select which of the 16 32-bit math registers receives the output. I think these are multipliers, aren't they? These are only multipliers by the looks of things. I need to check on that. I'm not entirely sure how that works. Yeah, okay. How many are you missing from that series? From the and what is the series? Do you know what it is? Somebody tell me what they think that series is. I think I know which one you're missing. Yeah, the bands one. I think I am going to finish that, but I'm not going to play Res tonight. I'll play Res tomorrow though. I have to check Annoyed. Acronyms. Okay. Bad names that are acronyms. Yes. Kind of. Almost. That's like 99% of the answer. It's not quite the answer. If you change one word in the phrase band names that are acronyms, and you've got it. Okay, so I'm not sure how this math unit works, so I'm not gonna because I have a funny feeling it's only for multiply, unless there's a switch somewhere which can define. It doesn't look like there is. Oh, I didn't realize that division busy, multiplier busy. Ah, interesting. Yeah, I'm gonna finish at past. I think we've done pretty well tonight. Hopefully you guys have got some kind of useful information from this. I realize it's been quite a lot of stuff to take in. So um, apologies if that's been a bit much, but I will upload these videos at some point. I'm probably going to do a catch up this weekend with the videos. And go through what I've got recorded and just kind of quickly get them onto YouTube. I'm going to start doing less and less of the YouTube, but I will try and drop as much as I can on there. Just I'm not going to go crazy. So, um, any news when the final pick and mix will be released? Um, so I kind of answered this a little bit the other day. So the game is 99% complete. There are a few little things I want to polish on it. I want to just kind of uh, double check the level order and add some kind of credits and stuff in. There's not a lot left to do. I just need to find the time to do it. I just haven't had time to do it. So I need to find myself a couple of days where I can just do it. It's not going to be something I do on stream, but I just need to find a bit of time to do it. I've been extremely busy with work, so I'm doing a lot of stuff at work, and I'm learning some new stuff, and I'm having to do kind of certification as well, which is kind of taking a lot of my time up during the workday. And then also my focus has very much been on getting the Mega65 um, as close to perfect as we can. So with a big focus on XEMU as well. Which certification? OSCP certification, Offensive Security Certified Professional. So it's basically hacking. It's a certification for hacking and pen testing. I've not even started properly yet, but my learning is kind of crazy at the moment. But I know it's going to get even more intense over the next 6 months or so. Um, yeah, it's going to be good. But yeah, anyway, I think we're doing quite well with this. I think we're in a situation now where we can proceed. I will probably do a little bit off stream to get prepared. What I will do though is if I do manage to get something working, I almost certainly will post a video of it because I'll just be so excited. But what I will do is I will put it to one side and I will redo it all again um, with on stream, so you can see the process of it. But I may do some experimentation on stream. Kali, yeah, it will involve Kali Linux. It's a bit of everything, but Kali Linux will definitely be involved. Um, okay, cool. Oh, there we go. That's the end of the rotary encryption machines. Pretty awesome. Somebody's going to kick himself when they work out what the missing band is. You're going to kick yourself. You're really, really going to kick yourself. Think about when I grew up. Think about what bands were around when I grew up, and that should give you the idea. Anyway, I think I'm going to call it a night there then. So let me take a look for who to raid. Hayes is on. Not raided Hayes for a while actually. Usually we don't clash streams. It's usually he's streaming on different days to me. So let's just check. Oh, he's playing creatures as well. Oh, we have to raid Hayes then. Okay, cool. Let's raid Hayes then. Okay, awesome. Well, thank you for coming along tonight. We will do some Checkanoid tomorrow. So back to the C64 tomorrow. And then on Saturday we'll continue with this. So hopefully she'll have some more of this on the go on Saturday. We'll play around probably with the math unit. Then I'll do some tests on the math unit, but I think that's where going to be what's going to be where our optimizations come from. But yeah, thanks for joining, everyone, and I shall see you all very soon on Saturday. I'm going to go and just pass out in my bed, so yeah, anyway, all right, let's go and raid Hayes now. Take care, guys. Thank you for coming. Thank you for all the bits and all the all the subs and everything. You're all absolutely completely mental, and I'll see you on Saturday. Cheerio.